day third years. In Module 4, we will mainly discuss chemical equilibrium. You may recall that you have already encountered this topic during your analytical chemistry course, so some of the concepts that we will talk about here will serve as a review of what you have already learned. In this lecture, you will learn to predict the direction and equilibrium of reactions based on the reaction Gibbs energy, calculate the equilibrium constant of different reactions, and to determine the effect of different disturbances on reactions in equilibrium according to Le Chatelier's principle. So first, let us start this discussion by describing how chemical equilibrium is related to Gibbs energy. Recall that generally, a spontaneous change at constant temperature and pressure proceeds towards the direction of lower Gibbs energy values. This can also be applied on chemical reactions wherein at constant temperature and pressure, a mixture of reactants tends to undergo a chemical reaction until the Gibbs energy has reached a minimum value. And this condition corresponds to a state of chemical equilibrium. At this point, forward and reverse reactions still occur, but at the same rates. So to identify the equilibrium composition of a certain reaction mixture, the Gibbs energy of the mixture is calculated and the composition that corresponds to the minimum Gibbs energy is determined. Now, how do we determine the minimum Gibbs energy? First, let's consider this equilibrium reaction, where reactant A is converted to product B. Let Xi represent the extent of reaction reported in units of moles. If an infinitesimal amount of dxi of A is converted into B, we can get the change in amount of A, dn sub A, equal to negative dxi. Negative because A is being consumed. Likewise, the amount of B that was produced, or dn sub B, is equal to positive dxi. Now, we define the reaction Gibbs energy delta G sub R as the slope of the graph of Gibbs energy plotted against the extent of reaction Xi as shown in this equation. We know that Gibbs energy is also equivalent to chemical potential, wherein the change in reaction Gibbs energy is equal to the change in chemical potential as the reactants are turned into products. Now that we know these relationships, let's find out how we can use this to determine equilibrium. Shown here is a plot of Gibbs energy versus extent of reaction. Since chemical potential varies with composition, then it is expected that the slope of this plot, that is the reaction Gibbs energy, also changes as the reaction proceeds. The direction of spontaneity follows the direction of decreasing Gibbs energy. Chemical equilibrium is described by the minimum Gibbs energy. We know that at the minimum point, the slope is equal to 0, and thus delta G sub R is also equal to 0. This means that at this point, the chemical potentials of A and B are equal. Note that this further shows the purpose of chemical potentials. It corresponds to the potential to undergo chemical change, and when these are in balance, chemical equilibrium is achieved. When the chemical potential of the products is lower than that of the reactants, the forward reaction becomes spontaneous. This is signified by negative delta G sub R, and this is called exergonic reaction or work producing. On the other hand, when the chemical potential of the products is higher than that of the reactants, then the reverse reaction is spontaneous. This shows that a reaction wherein delta G sub R is positive, and this is called endergonic reaction or work-consuming. Take note that when the equilibrium occurs, not all reactants has been converted to products. Both reactant and products are present in the equilibrium mixture. The position of equilibrium in the plot can tell you whether reactants are present in greater amounts, such as shown in the plot of case 1, or if products are favored as shown in case 2. Now that we have established the background of chemical equilibrium, let us discuss how we apply thermodynamics to the description of equilibrium. Let us consider a general reaction with stoichiometric coefficients and not just 1:1. The stoichiometric coefficients are presented as V sub j, such that the amount of change of reactants or products are given as dN sub j is equal to V sub j times the extent of reaction d xi. Take note that V sub j is negative for reactants because they are being consumed, while positive for products since these are formed. At constant temperature and pressure, delta G sub R is given as the summation of V sub j times the chemical potential of substance J. This is the general form of the equation of delta G sub R in terms of chemical potential. Recall that for the simple equilibrium reaction of A to B, delta G sub R also followed this equation. Now, to make progress in this derivation, we introduce the relationship of the chemical potential and activity of substance J as shown in this equation. When this is substituted to the equation of delta G sub R, the resulting expression becomes this. Note that the first term, this one, which is in terms of standard chemical potential, is just equal to the standard reaction Gibbs energy or delta G naught sub R. And following the rules of logarithms, V sub j in this term becomes the exponent of A sub j. Thus, we can simplify our equation to this. Following the rules of adding logarithms, wherein ln x plus ln y and so on is just equal to ln xy and so on, we can express the summation of ln terms as the ln of the pi function of activities. The pi function denotes the product of what follows it. It is similar to the summation function, but instead of adding the terms, we multiply them. So the reaction Gibbs energy expression results to this one. The pi function of the activity raised to V is termed as the reaction quotient. This is the ratio of the activities of products and that of the reactants. It is worth recalling here that the value of V sub j becomes negative for the reactants, which leads to it being in the denominator. Now, the reaction Gibbs energy of a reaction at any arbitrary stage is given by the standard reaction Gibbs energy plus RT times ln of the reaction quotient Q. The standard reaction Gibbs energy can be calculated from standard Gibbs of formation, which you can find in literature. We know that when the reaction is at equilibrium, delta G sub R is equal to 0. This means that the activities are at their equilibrium values, and we will define the thermodynamic equilibrium constant K0 as follows. This means that K0 is the value of the reaction quotient Q at equilibrium. Take note that activities are dimensionless, which means that K0 is also dimensionless. Also, because delta G sub R is 0, we can get the relation of standard reaction Gibbs energy and thermodynamic equilibrium constant as such. This equation is an exact and very important relation since this allows the prediction of the equilibrium composition of the reaction mixture. For practical applications, the activities in the reaction quotient and thermodynamic equilibrium constant expressions are usually replaced with measurable parameters such as concentration and partial pressures. These are established to closely approximate the thermodynamic equilibrium constant. When the activities are replaced by these parameters, we are now calculating the practical equilibrium constant K, which approximates K0. Keep in mind that although K0 is dimensionless, the dimensions of K will depend on its resulting expression. Take note that for pure solid and liquid, the activity is equal to 1, which means that these substances make no contribution to Q or K even if they appear in the chemical equation. These terms are usually omitted in the Q or K expressions. Now, before we go on to examples, let us first recall the properties of the equilibrium constant, which you have already learned in your analytical chemistry course. First, when the reaction is reversed, the equilibrium constant of the new reaction K' is equal to the reciprocal of the old equilibrium constant. Second, when the reaction is multiplied by a certain number, the equilibrium constant is raised to the power equal to that number. Finally, when you have a series of reactions wherein each step has its respective equilibrium constant, the equilibrium constant of the net reaction is equal to the product of the equilibrium constants of the reaction steps. Now let's work on this example. Calculate the thermodynamic equilibrium constant for the following reaction at 298 Kelvin if the Gibbs energy of formation of ammonia is negative 16.45 kilojoules per mole. Show how K0 is related to the partial pressures of the species at equilibrium when the overall pressure is low enough for the gases to be treated as perfect. To answer this problem, recall that the standard reaction Gibbs energy is calculated using this equation. If you look closely at this equation and remember that the value of V sub J is negative for reactants, this will also give you this equation which you encountered from Module 1. For this reaction, the standard reaction Gibbs energy is equal to this. Note that the Gibbs energy of formation for pure substances is 0. Therefore, the standard reaction Gibbs energy is equal to 3.29 times 10 to the 4 joules per mole. Now to solve for K, we use the equation relating standard Gibbs energy and equilibrium constant. Isolating K0 and substituting known values, we get K0 is equal to 5.85 times 10 to the 5. Next, we will use the expression of K0 and then relate it with partial pressures. K0 is defined as the pi function of the activities of the reaction substances raised to their respective stoichiometric coefficients. It is important to make sure here that the chemical equation you're working with is balanced properly. So K0 is equal to the activity of N2 raised to negative 1 times the activity of H2 raised to negative 3 times activity of ammonia raised to positive 2. After rearranging, we replace the activities with approximations for gas phase reactions, which is the ratio of partial pressure and standard pressure. Simplifying, we get this resulting expression. If we express the units in bars, then the standard pressure is just equal to 1 bar, and the K expression can be further simplified to this. If we evaluate the resulting dimensions of K for this expression, we'll see that it is given as bar raised to negative 2. To practice writing thermodynamic and practical equilibrium constant expressions, let's do example 2, wherein you are asked to write the thermodynamic and practical equilibrium constant expressions with units for the following reactions. For the first reaction, K0 is obtained by getting the product of the activities raised to their respective signed stoichiometric coefficients. Simplifying, we get this expression for K0. The practical equilibrium constant expression is obtained by replacing the activities with the ratio of partial pressure and standard pressure. Setting the pressure in terms of bars and standard pressure equal to 1 bar, we get this resulting expression with dimension of bars raised to negative 1/2. Similarly, for the second reaction, K0 is expressed in this form, while K is given by this equation with a unit of bar squared. Take note that the solid ammonium hydrosulfide has an activity exactly equal to 1 and may be omitted in the expressions of K and K0. Lastly, before we move on to the next part of our discussion, let us consider example 3. Phosgene is formed through the reaction CO plus Cl2 yields CoCl2. At 668 Kelvin, the initial pressure of CO is 0.456 bar, and that of chlorine is 0.468 bar. The total pressure at equilibrium is 0.586 bar. Calculate the equilibrium constant for this reaction. To solve this problem, you have to recall from your analytical course the technique we used called the icebox method, where ice means initial, change, and equilibrium. We will also consider here the total pressure, which is just equal to the sum of the partial pressures of the substances in your system. The initial pressures are given in the example, and we write them in the initial row. At the start, COCl2 is not yet present in the system. The total pressure initially is equal to 0.924 bar. The total pressure at equilibrium, which is 0.586 bar, is also given in the problem. Then, the change in total pressure can be obtained by subtracting 0.586 from 0.924 bar, which gives us 0.338 bar. This translates to the change in partial pressure of each substance in the reaction. Remember, for the reactants, the change is negative, while for products, the change is positive. The equilibrium partial pressures are obtained by adding the initial and change rows. You can check that the sum of the partial pressures at equilibrium matches the given total pressure. To calculate the equilibrium constant, we substitute the resulting equilibrium partial pressures to the correctly written K expression of the given reaction. This gives us K equal to 22.03 bar raised to negative 1. In the last part of this lecture, we will discuss what happens to your system in equilibrium when it is subjected to certain changes in conditions. As you may already know, responses to changes in equilibrium are explained by Le Chatelier's principle. This states that when a system in equilibrium is subjected to a disturbance, the system tends to respond in a way that minimizes the effect of that disturbance. First, let's analyze the effect of pressure changes. We know that the reaction Gibbs energy, and thus K, is independent of the pressure at which the equilibrium is established. However, this doesn't mean that pressure changes will not affect the system in equilibrium. Note that even though K is unaffected, the concentrations and partial pressures of the substances are changed when the system pressure is varied. We can see this effect more by considering this equilibrium reaction of A dissociating to B and C. Its equilibrium constant is given by this equation. Recall that the partial pressures of a substance is equal to its mole fraction times the total pressure. Therefore, we can also express this K equation in terms of mole fractions and total pressure as shown here. So let's say that the system pressure is increased. Since we know that the value of the equilibrium constant remains the same, then this term containing the mole fractions must decrease by the same factor as the system pressure is increased. So we can say that if the total pressure of a gaseous equilibrium system is changed, the reaction system will respond by shifting towards the direction that will counteract that change. Now, how will the system respond exactly? Again, let's consider this equilibrium reaction with its equilibrium constant given in this expression. If the pressure is increased, or if the volume of the reaction vessel is decreased, the system will respond in a way that will minimize that increase in pressure. This is done by producing lesser number of molecules in the system. Therefore, the reaction will favor the side with fewer gas particles. In the given reaction, an increase in pressure will tend to shift to the reverse reaction since the reactant side has fewer molecules than the right. In contrast, when pressure is decreased or the reaction vessel volume is increased, the system minimizes the change in pressure by producing more molecules. Thus, it will favor the side that forms more gas particles, or the forward reaction for this particular example. If both reactant and product sides have the same number of particles, then this system will be unaffected by pressure changes. Now let's talk about the response of the system to temperature changes. Le Chatelier's principle predicts that if the temperature of the system is increased, then the reaction tends to shift in the direction of the endothermic reaction to absorb heat and oppose the increase in temperature. To illustrate, for exothermic reactions wherein heat is produced, an increase in temperature tends to shift the reaction towards the reactant side to minimize this temperature change. On the other hand, for endothermic reaction, an increase in temperature shifts the reaction to favor the forward direction to absorb the additional heat. To quantitatively describe this response to temperature, we will derive an expression that will show how the equilibrium constant is related to temperature. We start with the equation of standard reaction Gibbs energy equal to negative RT ln K. Next, transpose RT to the other side, then differentiate both sides with respect to temperature. Recall the Gibbs-Helmholtz equation from our past modules. Substituting this into our equation, we get the derivative of ln K with respect to temperature is equal to the standard reaction enthalpy divided by RT squared. This expression is called the Van 't Hoff equation. This shows us that if a reaction is exothermic, wherein reaction enthalpy is negative, then the slope d ln K over dt is also negative. This means that for exothermic reactions, the equilibrium constant decreases when temperature is increased. On the other hand, for endothermic reactions, the reaction enthalpy and slope are both positive, which signifies that K increases with temperature. A different form of the Van 't Hoff equation can be obtained by linearizing the expression. Note that the derivative of 1 over t with respect to t is equal to negative 1 over t squared, or dt is equal to negative t squared d1 over t. Substituting this in the Van 't Hoff equation, we get this expression, which is useful in evaluating the effects of temperature on K with a straight plot. We can also use the Van 't Hoff equation to get the value of the equilibrium constant at a different temperature by integrating the Van 't Hoff equation from ln K1 to ln K2 and from T1 to T2, and assuming that the reaction enthalpy is constant over the temperature range being considered. The resulting equation then becomes ln K2 minus ln K1 is equal to negative delta H sub r over r times 1 over T2 minus 1 over T1. Let's consider this example. Estimate the equilibrium constant for the synthesis of ammonia at 500 Kelvin if it has a value of 6.1 times 10 to the 5 at 298 Kelvin. Assume standard reaction enthalpy is constant over the temperature range. The formation enthalpy of ammonia is also given. To solve this problem, first we have to calculate the standard reaction enthalpy using standard formation enthalpies, similar to how we solved the standard reaction Gibbs energy in the previous example. Solving, we get negative 92.22 kilojoules per mole. K2 is calculated using the last equation we derived from the Van 't Hoff expression, which relates the equilibrium constants at different temperatures. Substituting known values, we get ln K2 equal to negative 1.7164. Therefore, K2 is equal to 0.178. This ends our discussion on chemical equilibrium. Thank you for listening and see you in our synchronous session.